Hello, algebra students. Mr. Lawrence here, and I'll let you know I'm feeling a little bit better, but my voice might not sound like me. But trust me, it is me. Who else would be doing this? All right, so today we're going to have our second part of our review video. This will be over number systems, and I've drawn a little Venn diagram here and tried to color code it for you to help make it a little bit easier. The Venn diagram starts in the middle here with this N, with the natural numbers, right? The N is for the natural. Remember, natural numbers go 1, 2, 3, and they go on forever. They have no fractions, no decimals in them. No fractions and no decimals. And I guess when I say no fractions or decimals, I mean ones that can't be simplified. Some of you might say, well, wait a minute, Mr. Lawrence, what about 8/4? That's a fraction. Yeah, but that simplifies to 2. So it looks like a fraction, but it really is just a natural number in disguise, okay? It doesn't have a 1/3. So, 1/3 can't be simplified. It's not a natural number because it doesn't come naturally when you're counting, so 1/3 is not included. All right? Now we have the whole numbers, and the whole numbers are just like the naturals, except they include 0 also. 0, 1, 2, 3, and so on. Now, an interesting thing to note, the reason I like this Venn diagram so much, if I'm in the pink circle or oval, am I in the green oval? Yeah, I sure am. This 2 is here, and it's also there. But notice if I'm in the green oval, it doesn't mean necessarily that I'm in the pink oval, because 0 is a member of the whole numbers, but you won't find a 0 in the pink oval. This chart works that way. The pink circle is inside the green, inside the orange, and inside this dark blue, and inside this kind of light blue rectangle. All right, well, let's get back to this. The integers are just like the wholes, but also include their negatives. So they go forever in both directions, and you'll go from -2, -1, 0, 1, 2, and then keep on going. So all natural numbers are whole numbers. All natural numbers are integers. All whole numbers are integers, but the chart doesn't work this way. It works left to right. It doesn't work right to left. All integers are not whole numbers. Name an integer that is not a whole number. How about -7? It's an integer. I would hit it counting in the negatives, but it's not a whole because the smallest whole is 0. Again, we still have no fractions or no decimals for these. No fractions and no decimals. And again, it's the ones that can't be simplified. Okay, if you want to say 7.0, but it simplifies to 7. All right, so no fractions and no decimals. Then we get to the Q, which is the rational numbers. And the rational numbers include everything you've seen before, plus decimals that either end or repeat. So for example, 2.571, 2 and 571 thousandths, it ends. 3.25 repeating. It repeats, okay? So the rationals include all integers and those decimals. They also include fractions, all fractions, okay, written with 2 integers, okay? So all fractions are written with 2 integers. The irrationals are over here kind of isolated by themselves, okay? They don't have fractions that can be written as 2 integers, and their decimals have 2 characteristics. They never end, and they never repeat. Okay, for example, pi is the best example we all know. Square root of 3 is 1. 6.1415 ... See dot, 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 it means it goes on forever without repeating. Altogether, these make up the real numbers. All right, these are the real numbers, all of these. The entire number line is a representation of the real numbers. You won't find any imaginary numbers on the number line. So let's check out these true-false statements. All whole numbers are natural. Well, if I could find one whole number that is not natural, this will be a false statement. I'm going to go back to my table. Hey, we talked about this 0. 0 is whole, but it's not natural. So this is a false statement. All whole numbers are integers, going back to my table. Let's see, the green circle is inside the integer circle, the orange one. So every member of the whole is also a member of the integers. So that is true. I can't find a counterexample. I can't find one number that's whole, but not an integer. All natural numbers are irrational. Well, that's just ridiculous because the irrationals are over here by themselves. Their group is isolated from these groups. So there are no natural numbers that are irrational. Okay. All irrational numbers are real. Well, let's take a look here. This group is isolated, but it is inside this big light blue rectangle, isn't it? That means they are real numbers. So that is true. Okay. Now we're going to do some operations with irrational numbers. And here I have the square root of 13 plus the square root of 13 plus the square root of 13. Hey, how many square root of 13s do I have? Well, let's see. I've got 1, 2, 3. What does it look like I'm doing from class? Oh, it looks like I'm combining like terms, and that I am. I have 3 square roots of 13. Oh, 3 square roots of 13 plus rad 6. So I'm treating these like variables. If it was x plus x plus x plus y, well, that would be 3x plus y, right? I did the same thing. I treated them like terms. Okay. Square root of 13 times the square root of 13. Well, remember, that would be the same as 13 times 13, which would be the square root of 169, which is 13. Oh, yeah. When I multiply a rad by itself, the rad goes away, remember? Yeah, let's try this one real quick. How about the square root of 121? Oh, no, that wouldn't be irrational. Well, I guess I could still do it. But let's go with the square root of 120 times the square root of 120. Okay, I think you'll realize by now that that's just 120. All right, coming down here, rad 13 minus rad 13 plus 7 looks like a like term situation to me. So I'm going to highlight the rad 13 and highlight that one. And then this one isn't a like term. I'll do him in his own color. And I think these two are going to cancel each other out. Yeah, so the answer here is just going to be rad 7. All right, and finally, rad 13 divided by rad 13. Well, it's 7 divided by 7. What's 1? What's square divided by square? It's 1. Oh, rad 13 divided by rad 13 must be 1. And it is. Remember, that's true for any number except 0. 0 divided by 0 does not equal 1. No, it does not. It's undefined. You are never, ever, 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 ever allowed to divide by 0. Never divide by 0. There is no definition in mathematics. Finally, the Pythagorean theorem, I think that's the last. Oh, then we've got to do our properties. Sorry about that. Pythagorean theorem. A squared plus b squared equals c squared. And remember, c is the most important part of this formula. I find c by going to the right angle and drawing an arrow or a ray. And there's c. Okay, so I'm going to fill out a squared plus b squared equals c squared. And I'm going to put 15 in c's place. I'm going to put 12 in b's place. And I'm going to put the unknown, the variable x, in a's place. And then I'm going to use my equation solving skills and see if I can figure out c. All right, looking good so far. And then I'm going to subtract 144 from both sides. I'm going to get x squared, and that's going to equal 121. Now I have to take the square root of both sides, not square both sides. Remember, some of you say square both sides. That's absolutely incorrect. I have to take the square root of both sides. Square root of 121 is 11. Now it does have two square roots, but since we're talking about the side of a triangle, we can't have a negative length, and so we'll only use the positive answer. For this other Pythagorean theorem problem here, I go to the right angle, I draw my ray. Looks like C is my unknown, so I'm going to take 5 squared plus 5 squared, and that'll equal x squared. So this will be 25 plus 25 equals x squared. So that'll be 50 equal to x squared. Now 50 is not a perfect square. I do need to take the square root. In this case, I'm going to use a decimal approximation. I know that the square root of 49 is going to be 7. Square root of 50 is going to be a little bit more than 7. I'm just going to kind of guesstimate, and then I'll go to my calculator. I bet it's going to be about 707, but 7 and 700ths. But let me go to my calculator. You can do that too. And look, I got 7 and 700ths, okay? I knew that from experience. That's a rounded to the nearest hundredth answer, by the way. So x would be the wavy equal sign I need, not the regular equal, because it's only a decimal approximation, 7 and 700ths inches. Now, I got to warn you, I may not say use the Pythagorean theorem. I'll be expecting you to look for a right triangle on your paper and know to use it. All right, the distributive property, make sure you recognize that if I have 3x times the quantity of 4x plus 5, and then I'm going to distribute, that'll be equal to 12x squared plus 15x. You'll be expected to recognize when the distributive property has been used. So you look for a number in front of a quantity, and then you look for the numbers that were in the quantity to have gotten larger or smaller. How could they get smaller? Somebody's asking. Well, what's 1/2 times 8x minus 6y? Well, half of 8 is 4x, and half of negative 6y is negative 3y. So you see they could get smaller if I'm distributing a fraction. All right, the commutative properties, and there's two of them. There's one of addition and there's one of multiplication. You can, they're done the same way. Come on in. You can do them the same way, but you have to indicate which operation is being used. The commutative property says the order doesn't matter. It says you can change it. So 5 plus 3 is the same as 3 plus 5. That's the commutative property of addition. Okay, it might look more like this. 5x plus the quantity of 2y plus 3z. And I'm going to say that 2y has a quantity plus 3z plus 5x. I just demonstrated the commutative property. Notice the order changed, okay? And you have to indicate if it's addition or multiplication. Multiplication would look like this. 5 times x times y, which is the same as 5 times y times x. That's the commutative property of multiplication. We tend to write it this way, so it's in alphabetical order, but mathematically they mean the same thing. Okay, the associative property. The associative property says the grouping changes. So you might have 1 plus 2 in a quantity plus 3, and then that would equal 1 plus the quantity of 2 plus 3. You can verify that by doing the math. 1 plus 2 is 3, 3 plus 3 is 6. 2 plus 3 is 5, 1 plus 5 is 6. See, I got 6 in both cases. This would be the associative property of addition. Of course, multiplication has it. If I did 2 times 3 times 4, that would be the same as 2 times 3 times 4, like that. Oops, can't see a 4 there. There we go. And again, you could do 12 inside the parentheses. 2 times 12, 24. And then you could do 6 times 4, which would be 24. That's the associative property of multiplication. All right, that's the video for tonight. Hopefully you're studying and preparing for this test. It'll be very important to many of you. Mr. Lawrence signing off. Have a good night, everybody.